So another characteristic we want to talk about in our polynomial functions, if we're looking at them, let's say, algebraically, we can evaluate or we can analyze a polynomial function based on its degree, and then that degree tells me how many possible turning points I have occurring within that function. So this rule just says that if I have a polynomial function of degree n, then the graph has at most n minus 1 turning points. Okay, so if I have a polynomial function of degree n, then it can have at most n minus 1 turning points. So let's go look again at a graph we've been carrying through in some of our videos. This function right here was a 6th degree polynomial. Okay, so this 6th degree polynomial would have at most 5 turning points because 6 minus 1 is 5. So we could say that if I was just looking at the polynomial, that I know that it might have, or it would have at most 5 places where it changes direction. That's what the turning point tells us. If you're looking at the picture right here, you can see, however, that we have 1 change of direction, 2 change of direction, 3 changes of direction. So this 6th degree polynomial only actually has 3 turning points, but just analyzing it algebraically, we get an idea that says, well, if I didn't graph it automatically and do some calculus on it basically, I would know that it was going to have at most, it can't have any more than 5 turning points. And again, you really study that a little bit more in calculus, but we have some sort of idea of what's going on when we graph it just by this rule here. So let's practice that. We have an example that I want to look at together. It says that I would like to write the polynomial function for the graph that's shown. Okay, so I need to kind of take all of this stuff we've learned so far and write the polynomial for this right here, and then we're going to check it using the graphing, like a calculator or something. First things first, if we see here the n behaviors are both going off in the same direction. They happen to be positive, so we know that this is exhibiting even-like power. So this is an let's spell it right, an even-powered function, because they both go off in the same direction. So by using the turning points, we're going to determine the degree of the polynomial. So we're going to use that definition of turning points to determine the degree. I can see here that this polynomial function changes direction 1, 2, 3 places. So we have 3 turning points, and the degree of the polynomial minus 1 gives me the number of turning points. So by solving for n, which we can see that n is equal to 4, that tells me that this is a 4th degree polynomial. Okay, so n is the degree of the function. And that goes back to what the n behavior looks like, that if it is even powered, it would go off like in this same direction, and a 4th degree is even. Now let's address the roots and their multiplicities. So let me make this just a little bit bigger in case you can't see it. I have roots occurring in this picture. I have roots occurring here at -3, -1, and +2. Okay, so I have them occurring at -3, -3, -1, and +2. So that means I have x plus 3 in its factored form, x plus 1, and x minus 2, excuse me. But what are they doing at each of these roots? At -3, we are going to cross, which means that I have an odd power, right? So this needs to be odd. At -1, I am touching, so this needs to be even. And at +2, I cross, so this needs to be odd as well. So let's go back to a smaller screen. Now, if I know that the total degree of my function has to be a 4th degree polynomial, how do I write that given the multiplicity of my function? This is going to look like x plus 3, an odd power. Let's try a 1 for the odd, a 2 for the even, and a 1 for the odd. Hopefully you can see that. So if that's the case, what I end up with is x plus 3 to the first, x plus 1 to the second, x minus 2 to the first. And that does give me odd, even, odd. Now let's count it up and make sure it's 4th degree. So I have 1 plus 2 is 3 plus 1 is 4. Okay, so that's the polynomial now that I'm looking at. Okay, so my polynomial function, we'll just scoot it down there. My polynomial function looks like this so far, but the only thing I'm missing is I need to know what the leading coefficient is going to be, because that'll affect the actual shape of my function. So to find the leading coefficient, let's just go back over here, and any point on this graph, any point I choose, let's say that's 0, -3. If I were to plug in 0 for x, I would get back 3, right? I would be able to solve the function basically, or if, let me state it a different way. If I put in x, I should get back y, because this point is a solution for this equation. So if ultimately I'm trying to solve for an a, we do like we've done in previous sections, and we're going to use that point that I labeled on my graph, 0, -3, because that was just an easy point for me to recognize. And we're going to substitute into this equation to solve for the variable a. So it looks like this. If I were to let -3 be my f of x or y value, then I have a times, and everywhere in my function I have an x, I'm going to replace it with a 0. So I have 0 plus 1, 0 plus, oh wait. I have 0 plus 3, 0 plus 1 squared, 0 minus 2 to the first. Okay, so let's simplify this. We get -3 is equal to, this is 0 plus 3 is 3 times 1, which is still 3, times a -2, which would be -6a, if I were to multiply all those together. And look what that made, a really simple equation for me to then solve for the variable a. So I find out that a is equal to 2. So my leading coefficient for this entire function is not 2. What was I thinking? If I divide both sides by 6, I get 1/2, not 2. So my leading coefficient is 1/2, not 2, 1/2, and I can then see how well does my found function, 1/2 times each of these three things, how well does that compare with the graph that we have right here? So let's go to Desmos and check it out. So I graphed this function, the one we created, using Desmos, and I screenshotted it here under the graph that we were using in the notes, just so that you could look at it. Now, of course, you could graph this function as well in your graphing calculator to just check it. I just did it using Desmos because it was easier. But I can see that it is the exact same function because I have x-intercepts or roots occurring in the same places as the original graph. I have a y-intercept occurring over here, or an additional point, let's just say, an additional point occurring here at 0, -3, and then of course you can see that the end behaviors are similar as well. So we did create the equation, or the polynomial associated with this graph. So in keeping with the form of our other problems, I have one for you to try as well. So pause the video, practice this on your own, and then let's see if we get the same answer. Okay, so let's go over this. We can see that this function is moving off in opposite directions. That means we're dealing with some sort of odd-powered function. It has two turning points, so we can determine using the turning point rule that this is a third-degree polynomial. We have intercepts or roots occurring at 0 and 1. Now, how do we handle that? For my 0 root, it would look like x minus 0 if we were to write it that way, which really just comes out as x. And then we have 1, the 0, 1, which looks like x minus 1. Now, because we are actually crossing at 0 and touching at 1, we have an odd power for my x term, or here, we'll look at it over here. We have an odd power here for x, which we can say to the first power. We have an even power for the x minus 1 because we're touching. So those would look like an x to the first and an x minus 1 to the second. Here in this step, we're going to try to find a. Now, if you tried to plug in this point 0, 0, like we did in the previous example where this is one of my y-intercepts, it didn't get you what you wanted, did it? Okay, so instead we're just going to choose another point along this graph, because remember, any point that lies on this graph is a solution to this function. So we are given the point 2, -4, so that's the number I'm going to, or that's the ordered pair I'm going to use to solve for a. And when I do, I can see that a ends up being -2, which makes sense because that -2 flipped this function, didn't it? It flipped it across the x-axis. So we have a -2 for a, x minus 1 quantity squared. I went over here, you can see that I graphed it, and indeed it is the same function. I'm crossing at the origin. I have a touch over here at 1, and then down here I am passing through the point 2, -4. So we can, from the graph, we can actually create the polynomial that we're looking at.